Today we're going to review our symmetry rules when it comes to the coordinate plane and functions. And there are 5 basic symmetry rules we're going to go over, and you'll have to memorize these rules. This is review from last year, so we can apply them algebraically and test for symmetry algebraically. So the first one is symmetry about the origin. And that means if a point is up in the first quadrant, then if you reflect it through the origin, another point should be down here in the third quadrant. So the rule for that looks like this. If x and y is in the function as a point, then negative x and negative y will also be on that function or relation. So if I have xy up here, then I would also have negative x, negative y. And you should be able to connect those 2 points through the origin. There's an x. So that is symmetry about the origin. It's equivalent to rotating 180 degrees. The next 2 are symmetry about the x-axis and symmetry about the y-axis. And these are counterintuitive. If you're symmetric about the x-axis, then you are not a function. You would be a relation because you would fail the vertical line test. And the rule for that, if I have a point up here in the first quadrant, if I'm symmetric about the x-axis, that means I could fold it over the x-axis and I would have a corresponding point in the fourth quadrant. So if I start with xy, if that's on the relation, then x negative y is also on the relation. So those 2 points would work. For the y-axis, if I have a point over here in the third quadrant, then I would have a corresponding point over in the fourth quadrant. So you are reflecting over the y-axis and changing the x value. So if I start with xy, I'm going to end with negative xy. So those are the rules for the x-axis and the y-axis. The last 2 rules are for our 2 special lines. We have the line y equals x. That's a 45-degree angle. So I'm going to dot that in here, or dash it in. That's the line y equals x. And then the line y equals negative x has a slope of -1, so it's the other 45-degree angle. So we can be symmetric about those 2 lines, and they have special rules to them. If I'm symmetric about the line y equals x, then I'm basically switching x and y. So if I'm up here, then I would cross this line and have a corresponding point down there. So the line connecting would be perpendicular to the line y equals x. So if I start with xy, I would end up with yx. And that's a very important rule because what that's going to do, we did algebraic inverses yesterday. And to find the algebraic inverse, we switched x and y and then solved for y again. So what we'll see eventually is graphically inverses are reflected over that line y equals x. And you can see here we switched x and y to find the corresponding point. So if this point is on the original function, the corresponding inverse would be this point where we switch x and y. Finally, y equals negative x is similar. Again, I'm reflecting. I'm at right angles to that line. So if I start with xy, I'm going to negate both of them and switch them. So that would map to negative y, negative x. So those are the 5 rules of symmetry. And you have to memorize those 5 rules because we're going to use them to test for symmetry. And what we're going to do next is take one example and test them through all of those rules. And then we're going to work more on that in class. So here we go. We have a function x to the f of x is x to the 4th minus 2x squared plus 2. I want to determine the symmetry. I want to know if it's symmetric about the origin, the x-axis, the y-axis, y equals x, and y equals negative x. And to do that algebraically, I could graph it and take a look, but let's say we don't have our graphing calculators with us, or maybe it's a relation instead of a function. which is more difficult to graph. So for this one, we're going to try all these algebraically just by using the rule. And what I mean is, instead of xy, I'm going to replace my x with negative x, and I'm going to replace my y with negative y. And if that still yields the original, then the rule works. So for every x I see, I'm going to replace it. Instead of x to the fourth, it's going to be negative x raised to the fourth power minus 2 times negative x squared plus 2. And on the other side, I'm going to replace that f of x with negative y. Since that's originally y, it's now negative y. When I simplify everything, I need to come up with the same expression as the original for this symmetry to work. So let's go through this. I have negative y is equal to, whenever I raise a number to an even exponent, my end result will always be positive. So this negative x here, that's like a negative 1 raised to the fourth power, that's always going to yield a positive again. So this ends up being x to the fourth. The same thing here, I have negative x squared, so I'm squaring the negative x. That's going to yield a positive x, so minus 2x squared plus 2. Well, if I then divide through by my negative number here, I don't end up with the same thing. I end up with the opposite. So y is equal to negative x to the fourth plus 2x squared minus 2. So this is not symmetric about the origin. The rule does not work. So we're going to try it again with the x-axis. And what I recommend, as soon as you catch on, then pause this video and try it yourself, and then see how you do. And I'll take it from, and I'll go over it, and you can see if you got it right. So here's what we're going to do. We take this rule when it's symmetric about the x-axis. My x doesn't change, but my y does. So I'm going to replace y with negative y, and everything else stays an x. So again, I end up with having to divide by negative 1, and I don't end up with the same expression. So this is not symmetric about the x-axis. Well, that's good, because I said it was a function, and if it were symmetric about the x-axis, it would not be a function. It would fail the vertical line test. So that kind of makes sense. All right, so try this one. What do you think is going to happen when I test the rule for the y-axis? If you look at this, I'm negating the x, but the y is going to stay a y. So my original function was x to the fourth minus 2x squared plus 2. So think about what's going to happen when I put in a negative x and I raise it to the fourth power, or I square it. So let's see what happens here. I have my y stays a positive y this time. My positive x is now negative, and I'm raising that to the fourth power, and I'm squaring it. So when I raise a negative value to an even exponent, it always ends up positive. I end up with positive x to the fourth minus 2x squared plus 2. And if you look, this guy is the same as the original. So what that tells me is that it is symmetric about the y-axis. So for the y-axis, it's a yes, the rule works. So now before we even start with y equals x, we're going to switch them around. Y maps to yx. So what you have to do is replace the y with an x and the x with a y. And that gets a little goofy. If I were to do that, it looks like this. X is equal to y to the fourth minus 2y squared plus 2. This is nowhere near the same as this. Even if I were to try to solve for y, I would not end up with the same expression. just for starting out, if I were to subtract the 2 right away, it's not going to work out. So this is not symmetric over the line y equals x. And the same thing for this one. If I use this rule, that means my y value is now negative x, and my x value is now negative y. We can do a little bit of work here because we can square our negative values. But I'm still not going to end up with the original. This is y to the 4th minus 2y squared plus 2. That's almost the same as what we had before. If I were to solve it, it would get a little wacky. I might have to do, I don't know, some goofy stuff. But there's no way I would end up with this original expression again. So my function is not symmetric about the line y equals x or the line y equals negative x. And that's typical for most polynomial functions, is that they will not be symmetric about those lines. But let's look at one that might be symmetric about those lines. So this function is called a reciprocal function. And it's a reciprocal function because if I were to place the f of x with a y, we have y is equal to 2 over x. There's a reciprocal relationship between y and x. These are typically symmetric about the lines y equals x and the line y equals negative x. So if I were to test the line y equals x, that means xy would map to yx. Let's take a look at that. That means I'm switching these two and solving for y again. Well, if I multiply both sides by y, I get y times x is equal to 2, and then if I divide by x, I get y is equal to 2 over x. That works. So that's an example of a function that is symmetric about the line y equals x. Now we can try the same thing with y equals negative x. My rule is negative y, negative x. So when I substitute things in, I get negative x is equal to 2 over negative y, and you're almost back to the same thing because what happens is your negatives will reduce down. If you divide both sides by negative 1, you end up with x is equal to 2 over y, and then when you solve, again you're back with y is equal to 2 over x. So a reciprocal function is actually symmetric about the line y equals x and the line y equals negative x. Some of these functions you can graph and figure out, but in this lesson we are working on testing algebraically. So we will test more functions in class algebraically for the 5 lines of symmetry.